exponential function, it is always in this way. We have y is equal to c, it is a constant, a raised to x. Okay, and a is always greater than 0, but a cannot be 1. I will show you later why a cannot be 1. And y is what we call the new value. C is the original value. And a is the rate of change. And x is time. There are a lot of ways to put this. Sometimes you can see y is equal to y sub 0 multiplied by a raised to x. Or if it's temperature, so time, and the temperature over time is equal to the original temperature multiplied by a raised to t, which is time. If it's about bacteria, then we have bacteria over time, and then we have how many bacteria from the start, and then we have a raised to t. So it depends. I'm going to use now the GeoGebra to see you how it looks like. We have y is equal to, as I said, c multiplied by a raised to x. And it says that I'm going to, it's in Swedish, of course, but I'm going to use a glider. As you can see now, a is equal to 1. I said that it cannot be a is equal to 1. Why? Because we don't have any changes. As you can see, it's just a line, a straight line. No changes at all. Okay? So when x is greater than 1, here, greater than 1 I should say, then it is increasing. It is growth. So if you have money in the bank, it depends upon the interest rate, then it is increasing. Okay. If it's near 1, then it doesn't increase that much, as you can see. But if it's 2, for example, it increases, and it increases more. If it's less than 1, then it is decreasing or decay. Then you need to use that in bacteria decay or carbon activities like that in science. What more I can say? C is a constant. So if C is 5,000 or 5 at this time, the original, then it is always there. It is in the y-axis. What more I can say? It goes near, very near to 0, but it doesn't touch y is equal to 0. So never. So if I'm going to expand this, as you can see, it doesn't touch. Very near, but it doesn't touch. So, as you can see there. Okay? It's the same also when a is more than 1, when it is increasing. It looks like it touches y is equal to 0, but it doesn't. There you go. It doesn't touch. There you go. Okay? So that is very good to know. It doesn't touch y is equal to 0. Okay? And the c is the original value. Okay, let's see if we can solve some example here. An example here, use the graph above to estimate the value of 2 raised to 1/2 or square root of 2. So remember that you have y is equal to 2x here, as you can see. I hope you can see that. There, y is equal to 2x. That means x is equal to 1/2. So you need to take 1/2 there and then put there. Okay. And then 1, 2, 3, 4, 5. It's there. There. It's almost 1.4. 1, 2, 3, 4. Yeah. And 2 raised to 0.8. 0.8 is here. There. So if I'm going there, it's almost 1.75, for example. And then you can do the rest. Use the graph above to estimate the solution to 0.6. As add to 3, so you need to look at 3, then it's there. I will use red so that you can see 3 here, there. Then it should be 1.1, 2, 3, 4, 5, 6, 1.6. X should be 1.6 here. 1.6. And 0.6, let's see here. 0.6. Here, no solution. There is no x because x starts with 1. So no solution. So use the graph of y is equal to 2x. Raised to, y is equal to 2 raised to x, sorry, to explain why 2 raised to x is equal to 0 has no solution, because it doesn't touch. Sorry, I didn't see that. 0.6. 1, 2, 3, 4, 5, 6 there. 2, 3, 4, 5, 6 here. There you go. X is negative 0.8. Almost. Okay? About. But yeah, as you can see here, y is equal to 0. This is your y. This is your y. So y is equal to 0. As I said, it doesn't touch 0. Y is equal to 0. That's why there is no solution. And application of exponential function is what we call growth and decay. That is what I'm going to discuss in my next video. See you.